Okay, we are going to start in a moment, so let's try to see whether everything works fine. It seems that people are still joining, so maybe let's wait for a minute or two.
Yeah, sure.
Okay, welcome everyone to our ITMP seminar. And today we are going to have a talk by Ariel. It's going to be about production of massive particles out of massless free fields. So please start.
I cannot share the screen. So.
Just a second. So it should work now.
Cool. Then can you see the presentation?
Yeah.
Okay. Yeah. Hello, everyone, for coming. Mitya just made me notice that maybe this title is a little bit confusing and maybe contradicted, because of course it says that the field is free, but it's also say that it decays. But okay, it means that it is not free, but I mean that it is initially asymptotically free, like a particle which is asymptotically free at the beginning, then it decays in other states. Okay, let's review first the simplest thing about these decays, which is the decay of a single particle state in quantum field theory. Let's say we have this phi naught, which is the decaying particle. And let's suppose that there is a theory where it decays into this other phi 1, phi 2, etc. And then here we have the Feynman diagram. And we know that one condition that needs to be satisfied for the decay to occur is that the momentum and the energy must be conserved, right? Then in this case, when we have just a single particle state, at the decaying particle is just a single state, and after it decays, we will have soon another asymptotically free states, which are the produced particles. Then in that case, this omega corresponds to the energy of these particles and the energy of the incoming particle, because they are free in the final state. Then one can compute the decay rate with the usual formula. And where this SFI is the scattering matrix, which is given by this formula below. And okay, one can find that the energy momentum the energy momentum conservation is required for the decay. Right, this M is the Feynman amplitude. Okay. Okay, we are going to study this decay in this simple toy model, where we have this interaction Hamiltonian given by this. We have like phi is the decaying field, and chi corresponds to the field which is produced. Then we are interested in the process where phi decays into maybe two states. And okay, we assume that at the beginning, we produce this phi field. Okay, we assume it behaves initially like a free asymptotic state with a single momentum. We are just work out the most simple scenario with just one momentum p. Okay. Okay, m phi is the mass of the phi field, and m chi is the mass of the chi field. Okay, we define this omega like this which is of course the energy if the field is free, the energy of the particle of the quanta if the field is free, and this omega, this big omega, which is the same for the chi field. Okay, we're going to study this process. We have an incoming phi with momentum p, and it decays into a chi with momentum k, and the other one with momentum p minus k. Okay, here the momentum is already conserved, okay, in every decay. And we define this epsilon k as this like this, we notice that if the final and the initial states are free, epsilon must be 0, or epsilon 0 means the energy conservation, right? Okay. We will study this, this process in 2 scenarios. The first scenario is when phi is a 1-particle state. And the second scenario, which is what is important in this talk, is when phi is highly occupied. Okay, it has a high energy density. Okay, we will study these 2 scenarios in 2 opposite cases. The first case is when phi is massive and chi is massless, and the other is the opposite, when phi is massless and chi is massive. Then the first case is, of course, discussed in the literature. It is known, and everybody knows that it happens because phi is massive and it can decay into massless particles, right? But the second one, as far as I know, it has not been discussed. I hope it has not been discussed. And this is the new thing. Okay, this is the new stuff. Let's say, okay, in scenario 1, when the initial state is a 1-particle state. Okay, as said before, the scattering matrix is given by this, and it requires the energy conservation and the momentum conservation. Then epsilon equals 0 is required. Then for case 1, for instance, we can go to the rest frame of the decaying particle, and the decay occurs if the momentum of okay, in this scenario, the both particles has the same k in different directions, of course. And if it is m phi over 2, then we can have the process, and the decay rate is given by this formula. Okay, that's known. In case 2, epsilon can never be 0. We know that. Okay, there is no frame where it can be 0. There is no energy conservation. Then the decay rate is just 0. Okay, let's go now to the scenario 2. Then we assume the decaying field as a very dense field. It's many particles in there. And okay, we model it like as a plane wave because it was created like a free field. Then, as it is very dense, we don't consider in this work the back reactions. Okay, we assume that it is very dense, and the loss in the energy loss is very small. Then we focus rather in the produced particles or the produced field. Okay. Then now we write the chi field as usual. We expand in Fourier modes like this. Okay.
A question.
Yes.
So what's the why this is different just from creation by external field? So you apply external field phi as your external field. So it's known that you can the background field can decay. It can create particles in the background.
Yeah, but it's supposed that this phi, this external field, for instance, I have seen that if the external field is constant, right? For instance, in a external electric field, we can have it can decay, I think, but something is needed, like something that makes the energy conservation or something like that? Or
Well,
but here we have a lot of particles. We have, how to say, we have a cloud of particles which
yeah,
start to
it's
decay.
similar. It's similar. If you have constant field, it has infinite energy. So similarly here, you will kind of be relaxing energy conservation. Well, it's not the right word to phrase this like this, but anyway, sorry, maybe you just continue.
Yeah, but you made a good point. Maybe yeah. Okay, let's see at the end if that match what you're saying.
Yeah, I think it's not quite clear what you mean by like in a dense field. What do you mean by that? Like there is a background field which is, let's say, not small in the sense like non-perturbative. So you are considering what's happening, scattering in this background.
Yeah, for instance, okay, let's put it this way. For instance, I am familiar with the axion case where we have this axion cloud, which is at, let's assume it is at rest, right? And this axion cloud decays into 2 photons. Every axion can decay into 2 photons, and we have photon production. But here we have like the same, but we have particles moving at the speed of light. That's what I mean.
And what's the effect of presence of that cloud?
What's the what? Sorry.
Like, why is it important? Why it's important that there is a cloud, not a single axion?
Because the decay depends on the density. If as I showed,
yeah, and I guess the question is why is that, like, what is the effect of dependence? Okay, maybe you will come to that.
Okay, can I comment?
Yeah.
It seems that Ariel is considering, you do consider creation of particles by a classical field, classical background, and the only peculiarity so far that I see is that your background is oscillating in time, and yeah, so probably all the further discussion will be slightly different from, say, a constant electromagnetic field or something, because the background is oscillating. That's, yeah, probably my interpretation. But
yeah, I mean the thing is that I want to show that if this background is this fieldless is massless, it can decay if it is dense enough. That's my point.
okay.
Okay,
if they are sorry.
I think we understand what the problem is. So let's go.
Okay. Okay, then. Okay, we can define this A like this sum, and we define this alpha like a dimensionless parameter, which is related, okay, proportional to the coupling and the square root of the density, of the energy density. Then here we have this is like the equation. This is like the full equations for these A's, and there is no approximations here. The only approximation is that the how to say, the background is like keeps its energy density constant. This is the approximation. It's not true, okay, because it decays, but for the effects of the calculation, we can consider it as a background. Then we are going to find solutions in a more intuitive. Okay, I will use this equation later, but for now, let me find solutions in a more intuitive for me ansatz, which is this, when this chi is an amplitude which is time dependent and it oscillates. I don't know what happened. Okay. And okay, if we write this this chi in this way, we can compute the Hamiltonian of the system, and okay, it is written in this way, and we have this R. Then the important thing here is that if A variates slower in time than this this exponential, like these oscillations, then R is negative. We can neglect R in this. Then one can find that in this case the particle interpretation is correct, because we can define this A dagger A as the particle number density. I mean density in momentum space. But if R is not small, then I think the particle interpretation breaks down. Okay, in the case when we have just one particle state, this A is not, we compute in perturbation theory, and this A is not time dependent, right? But in this case, as the particles are produced because of this field, and they are not asymptotic free states after the decay, because the field is it interacts with the background, right? The produced particles interact with the background. Then it needs to be time dependent. Okay.
Yes, I'm sorry. I have a
yeah,
question. With this.
Yes.
Can you show your slide back? Yeah, you have this Hamiltonian, which is just the massive free Hamiltonian, right?
Yeah.
How come you have extra term R of t in this Hamiltonian? If you're there a dot somewhere, or what? I mean, it's a free Hamiltonian, so the free Hamiltonian has just one term in it, right?
No, this is okay.
Are you assuming that A changes in time, or what's going on?
Yeah. It is said at the beginning that A change in time.
And you have explicitly a dot in your R in your R?
Yes.
No, it's not very visible, but okay. Okay.
Yeah. So sorry. There is a. Do you think there is a problem with that?
No, I don't. I just don't see these dots.
I see.
The screen is not that visible.
Oh yeah. Sorry. Okay. Then the equations in this rotating wave approximation with, okay, I call it the rotating wave approximation, where this A variates slower than these oscillations, we can neglect the second derivatives of A, and we find these equations for the amplitude A. Then the advantage of this method is that we can find solutions. We can find the solutions in resonance or the solutions close to the resonance. Then in this way, we can neglect the fast oscillating terms in this equation. For instance, this term can be neglected. Okay, we can neglect it now, right? But we have these other terms. In this approach, we can, as I said, in this approach, the produced field we can interpret as particles, because this A varies slowly. Then we can, this epsilon 1, 2, 3, and 4, we can interpret these terms they are related to physical processes that can happen. For instance, this epsilon1, you can see that it is like some energy conservation, right? For instance, this epsilon2 is like what I defined before. If we have the field decay into two particles, and when epsilon2 is 0, we have like the energy conservation, right? But here, of course, we have a dense field, and the produced particles interact with the field, and okay, it cannot be interpreted as energy conservation, but if it is a small, okay, we are in resonance. And for instance, here, for epsilon1, it is interpreted as a process when it is small. I mean, when we are in resonance. When it is small enough, it is interpreted as a particle from the background that interacts with a chi particle with momentum k minus p, and it produces a particle with a chi particle momentum k, and so on with this. Okay, epsilon2 corresponds to the case we are worried in this. We concern where the field decays into this chi with momentum k and the other with momentum p minus k. Then, okay, of course, the epsilon4, it doesn't make any sense because it's like particles produced from nothing. Then, okay, it is always big, and it never approaches 0. Then there is no resonance here. But okay. Then the thing is that when some epsilon is much smaller than omega, the corresponding process is excited. Then, okay, what happened for t? Let's assume we have this field at t equals 0. And what happened for t bigger than 0, but close to 0? What happened at the beginning? Okay. And at the beginning, as we have only this field, this background field, the only process that can happen at the beginning is when this field decays into this chi field, because the other process, for instance, at the initial state of the other process contains chi's, right? Then the only one that doesn't contain chi's is the one that corresponds to epsilon2, right? Then this is the relevant at the beginning. Okay. Then, okay, in this epsilon, we define it like epsilon2, but I think it was defined before. And we just use the relevant terms in the equation, and we solve it. Okay, we find the general solution for this equation, and we have this. And we notice that what happened is that if we have this hyperbolic cosine and this hyperbolic sine, and if this S, okay, sigma is real and epsilon is real, then if S is real, then we have a parametric resonance. We have an exponential growth of the produced particles, and the field starts to decay through this parametric resonance.
Wait a second. What is sigma k and ck here?
Yeah, it was defined before here. Yeah, here. This is sigma.
Sigma. How is it that you have parametric resonance for sigma is just a parameter, right, in front of your parenthesis, right?
In front of my what? Sorry.
Parenthesis in the equation up in in here, right?
Yeah, it's just a parameter.
Yeah. So how do you get exponential growth of your amplitude? I mean, this is oscillatory equation. Sigma is just a number.
Yes.
How do we get the exponential growth of the solution?
Yeah, here, if you solve, I can show if you want, but if you solve this equation, you have exponential solutions, and you have cosines, hyperbolic cosines, and you also can have hyperbolic sine. For instance, if
this is a Mathieu equation, Valery Anatolievich.
Mhm.
With exponentially growing solutions, like in the earlier
Oh,
universe.
is it Mathieu equation? Really? I don't see Mathieu equation here.
Well, if a dagger is depends on A, is related to A, then it's similar to Mathieu equation. Like A, if it would include A in the right hand side as well, it would be a Mathieu equation, right?
yeah, if you one take the Mathieu equation and one makes that the function has an amplitude and an amplitude that varies slowly, and another term which oscillates fast, and one find the equation for this amplitude, and one finds something like this.
Okay.
Well, actually, can I ask also, because I am in doubt, because yeah, suppose you just redefine your A by multiplying e to the half of this exponent, A times e to the I epsilon t by half equals to A prime, okay? And in this equation, exponent will go away, and the time derivative, it falls on the exponent as well. So there will be an extra term in the equation. And then all coefficients in the equation would be time independent. I wonder, yeah. So that's how you solved it. Yeah. So, okay, sorry. Okay, so.
Yeah, that's how I solved it, yes. Okay, then, okay, of course, this solution is valid when this S is much smaller than these omegas, because this is what we assume to find this equation, okay, and the previous equation. Of course, we have to be careful that always our solutions are in the right limit. Okay, then the instability condition is just as S must be real, okay? For instance, if sigma squared is bigger than epsilon squared over 4, then we have the parametric resonance. But if epsilon squared is bigger than sigma squared, then okay, there is no parametric resonance, and we have just oscillation. And okay, I assume that in that case nothing happened. But the interesting case is when we have, of course, the parametric resonance. Okay. Okay, to analyze the instabilities, we define these dimensionless parameters. Okay, this k, it's like everything is normalized by this omega. Okay, which is the frequency of the field. And okay, this beta is like a frequency, but in normalized as well. And we also normalize this S. We call it a eta. Then, okay, now the rotating wave approximation is valid if this eta is much smaller than these betas. And the instability condition is when eta is real. Okay, for the case 1, okay, I want to recall that the case 1 is when the initial field is massive and the produced particles are massless, okay? Then in this case, the instability condition, it is similar to the axion problem or what happened in preheating, when we have this field which oscillates harmonically in time, and this is homogeneous. And the instability condition is given by these kappas in this range satisfy the instability condition, and we have for these kappas we have the exponential growth. If we translate this to k, we have this instability condition. Okay, then we notice that this k is centered at m/2, but we have some range, right? This k is not necessarily m/2, but it has some freedom with some boundaries, which are given by this g square root of rho. Then okay. Then this g square root of rho that somehow give the what is the bandwidth of the instability. Okay, then we notice that epsilon is 0. Epsilon in this case is 2k minus m, and it is 0 only for k equal to m/2. Then what happens is that if we think about if we think that the decaying field is produced is made only by one particle, we know that we need the energy conservation, right? Because the final particles are free. Then we need that epsilon must be 0. But in this case, the produced particles interact with the field, and for that reason we have the exponential growth, because we have the produced particles and they stimulate that the field keep decaying. Then we have this exponential. This is also called the Bose enhancement. Okay, what about the energy conservation? Because as I said, if the field is the decaying field is just one particle, we need this k equal m/2 to have the energy conservation. But here we have some freedom for this k. Okay, it's very small, this freedom, but it has not to be exactly m/2. We have this range, right, to have the instability. Then what happened with the energy conservation? Then we go to the Hamiltonian I wrote before, and okay, in this, if we compute the energy of the produced particles while they are produced, we find that this R is given by this. Then we have like a shift, like in this. Okay, this R contributes to this other term, and one can find that the energy, the average energy, is given by this. Then this part, this part is just the number of particles, of the produced particles, and they are multiplied by omega/2. Then what happened is that we have actually, as the number of particles is twice the number of the decaying particles, then we can see that we have energy conservation, that this energy is exactly the energy that was that the field lose. Okay. Okay, now I want to go to the case 2. To case 2, which is the one that is important, because in case 2 the field is massless. Then it's supposed that the massless field, for instance, if you have a massless particle, it cannot decay, right? It is stable. And as we showed at the beginning, if it is a single state, it cannot decay, right? Because of energy conservation. But okay, let's assume now that we have a cloud of these massless particles, and we model this at this monochromatic field. Then in case 2, we plot here this eta. Remember that for eta real, we have the instability. Then we can see that, okay, this mu, as I defined it before, but this mu is the mass normalized by the frequency of the initial field. We see that the instability happens, okay, in some range. But we just, okay, I will find analytical expressions, but we see here that this mu must be much smaller than 1, or the mass must be much smaller than the momentum or the frequency of the field. Okay, and to do this plot, I use that the angle between the decaying part, the produced particle, and the field is 0. Just to do this plot, and the alpha, which is related to the energy density of the decaying field, is okay 10 to minus 3. Then okay, what happened with the angle? In which angles the process can occur? Here I choose the mass, this mu, given by this, just to we are just analyzing what's happening, and we find that we also have instabilities. Okay, this is for different case. We also have instabilities, but we also find that it happens for angles very small. Then, so far, what we have that the massless field can decay. There is an instability if this angle, okay, the produced particles are ejected in some angle respect to the momentum of the free field, which has to be much smaller than 1. This is small, and the mass of these particles also has to be much smaller than the momentum of the decaying field. And this is another plot where I show this eta as a function of k or kappa, and for different angles. Okay, and okay, we can see that the wider instability happens for theta equals 0. As I increase the angle, we can see this green line and the red line. The instability is the bandwidth of the instability is smaller and smaller. Okay, then for big angles there is no instability. One can see that here as well. Okay, as we learn from these plots, we need, in this approach, we need the mass of the particles smaller than the frequency of the field, and the produced particles are produced in angles much smaller than 1. Then, in that case, we can calculate this epsilon, and we find this. Remember that epsilon is the parameter that where is it? Epsilon must be like smaller than sigma to have the parametric resonance. Then okay. Then as we saw that the maximum bandwidth of the parametric resonance is given when theta is 0. We take this parametric resonance condition, and we find what are the limits of the resonance, and we find that kappa must be in this range, kappa minus and kappa plus, which are defined by this. And we notice that the bandwidth is just this formula. Then to have the instability condition, we need that this delta K must be bigger than 1. Then it means that the instability condition is that this mu must be smaller than the square root of alpha. In terms of the physical parameters, we find that the energy density of the decaying field must be bigger than the momentum square, the mass to the fourth over 2 the coupling square. Then this is the most important result.
Can I ask a question about this
Yes.
result?
Yes.
The effective mass support in the for a given time, the effective mass of the chi particle, mass squared of the chi particle, is the original m high squared plus or minus whatever g times phi, right?
Yeah.
If you just look at the Lagrangian for your chi particle, then the effective mass for a given value of phi, you have m squared equal to m chi squared plus g phi, right?
Yeah, I think so.
So is this relation, is this condition of instability the same thing as saying that for some period of time, this effective m squared is negative?
Okay, like, you mean like what happened in the tachyonic instabilities, something like that?
Yeah, it's yes. Yeah, it's
Yeah,
tachyonic
okay.
instability happening at some period of time when the effective mass is negative, mass squared.
Okay, I will talk about that later, but okay, I think in the next slide, what happened is that you can see that this, okay, I don't know if it's to see, but I had to calculate, but I noticed that, or I demonstrated that this condition is Lorentz invariant. I mean, this rho over p squared is Lorentz invariant if the field is in case 2 when the field is massless. And then my question was, what happened if it is Lorentz invariant? What happened for a small p, right? When, for instance, if this calculation was made when the mass is much smaller than p. But what happened in the opposite case? What happened when p is much smaller than the mass? And okay, I look at the equations again. Actually, I can, yeah, this is a slide. Then in this case, when p is much bigger than m, okay, here we have the equation of motion. And in this limit, one can find the same instability. And here happened what you said. Here happens what you said, that we have like a negative frequency here. Then we have this instability. But in this case, I think the particle interpretation is not correct, because we cannot define the number, the particle number as the annihilation and creation operators. I think this is what I am thinking about this. But what you said is right. But one can see it one can see it in this opposite case when p is much smaller than, sorry. Yeah, when p is much smaller than m. Yeah.
Okay.
Okay. Okay. This is the previous part is what happened when the time is is close to t equals 0. What happened at the beginning. Now, I will show what happened for long time. Okay, I found that in case 1, when the initial field is massive, and the same happened forever. Okay, assuming that it is okay, there is no back reaction, assuming that the same thing happened. But in case 2, when the initial field is massless, other process start gradually become important. Then what happened is that, for instance, if we create a particle with momentum k, then this particle with momentum k annihilates with a particle from the field, from the background, and it can create another particle chi, for instance, with momentum k plus p. And so on. We have like a cascade of these processes. Then here I show a picture. Here I solve numerically I solve numerically this. Oh, sorry, what is it? These equations for A, to demonstrate that what I say is correct. And one can see that while the time elapses, we can see that the other modes, for instance, this mode k plus p and the mode k plus 2p and k plus 3p start to be important. Okay. Yeah, it was made for a single when k is p over 2. Then okay, and the other thing I have to say is that these dotted lines corresponds to the same calculation, but in the rotating wave approximation. Then we can see that they match perfectly. Okay, now I want to say the last part of my talk is I want to talk about the spontaneous decay. And okay, we define this okay, first order leading order is perturbation theory, the scattering matrix given by this. And okay, if we integrate between 0 and t, we get this sign of epsilon t over 2. And we know that, for instance, when the initial field is just, I mean, the initial state is just one particle, we know that the final states are free. Then one can just take this t as infinite, and this sign becomes a delta function. Then the energy conservation is required. But in this case, because of the exponential growth, the transition is not, one cannot take the transition as in an infinite time. Actually, the transitions happen in a time given by 1 over 2s, right? Because of the parametric resonance and the exponential, we have like the time of the transition. Then to compute the decay rate, we have to integrate until this time. Okay, we get this I get this formula. And for case 1, when the initial field is massive, we get the same as the usual decay rate, but multiplied by this n, which is the number of particles, the number of decaying particles, the number of particles of the background. Then if it is 1, okay, we recover the usual result. For case 2, when the field is massless, we get this result, and we have this this function, which is given by this formula, and it is plotted here in this figure, right? And we again see that the decay rate is 0 when for mu bigger than the square root of alpha, but if mu is smaller than the square root of alpha, that means that the main the main result that I showed, when the resonance is satisfied, we can find that there is we can define this spontaneous decay rate. And okay, I think that's all. Thanks for your attention.
Okay, thank you very much. So let's move on to questions. Are there any questions?
Equation. What do you think about application? Where do you want to apply your?
Yeah, that's the main question. I was thinking about okay, photon decay for sure. We have, let's assume we have a very dense, maybe laser producing photons. Yeah, laser produce photons, of course. Yeah, I wanted to see what happened. For instance, if these photons can decay into charged bosons, for instance, mainly charged bosons. And yeah, I was making some computation, and I found that maybe we can. I'm not pretty sure, but maybe there is density available densities to. I mean, because we need a very intense laser or a very intense photon field to have to make it to decay. But yeah, I think if we want to constrain mainly charged bosons by this mechanism, I mean, if you want to find constraints which are not exclude yet, I think we can do something with the current technology, but I'm not pretty sure. I have to do more calculation. But I think that's what I try to do it in the case when a photon decay into another photon and an axion, but the axion is very constrained now. Then I think the energy density we need is very high. Then I think it's impossible.
Okay, thank you.
What happens if your chi field that you create, if they're not bosons but fermions?
Yeah, I think that it doesn't. There is no parametric resonance because it happens only for bosons. It is actually it is a boson enhancement. Then because the boson has this property that they can occupy the same state, right? The boson condensate. Then it's related to this. Then in case of fermions, I think it doesn't happen. There is no exponential growth of the solutions, I think, of the produced field. But I'm not pretty sure.
Okay, maybe this is not exponential, but do you create pairs of fermions?
Yeah,
not
I was thinking that maybe
exponentially, but just
Yeah, maybe. Yeah, I expect that the solutions are not exponential, but are like a sine, and maybe we can have some growth of the. Yeah, maybe I have to do calculations. I'm interested in that as well.
I'm sorry, maybe I miss it, but what happened with energy momentum conservation if you have massless field phi and the massive field high? Maybe you say it, but I miss. Sorry.
Sorry, what's your question?
So you have massless field phi and the massive field high, and
Yes.
so you have n particles in the same state of field phi. Yes.
Yes.
Oh, no, okay. And from energy momentum conservation, how can it be phi, massless phi decay to massive high?
Yeah, that's like the main point of this talk, because if this massless phi is just one particle, there is no decay because of your argument, because of energy conservation. But if this phi is dense enough, we can have the decay. And what happened with energy conservation? Then here I show that actually we have the energy conservation. yeah, what happened is that these produced particles cannot be considered as free field. They interact with the background. Then it's more complicated what's happened. But if we make the computations, we can find the energy is conserved. It's not a problem. If it is dense enough, I mean, if you look at this condition, the energy density must be bigger than this, and then you can have the decay. If this is smaller, you have nothing.
Okay, thank you.
Let me ask a technical question.
Yeah.
I didn't see, if you go to your very first slide. Right, no, further on. I mean, where you have the equation for A.
For A. This A, the big A or the small A?
Yeah, this one, yes.
Okay.
This A is essentially annihilation operator, isn't it?
It is, yeah, it is operator, yeah.
It's basically, I don't see how you maybe, is there also a dagger in this equation?
In this equation,
A,
okay, you can have a dagger, but what happens is that A is chi plus chi dagger.
yes.
Yeah. Yeah, no, in this equation you don't have a, yeah, you can write this equation only with the A's. But A, for instance, every AK is related to a dagger in some, I think the relation is A dagger, A minus K dagger, I think, yeah.
So, I mean, you have to have a sort of mixture between A and a dagger, right? Between creation and annihilation operators. So in this equation, somehow you have to have both creation and annihilation operators. Is that correct?
Yeah, because A is chi plus chi dagger. And this chi and chi dagger are the creation and annihilation operators.
Is that right?
Yeah. Okay. We can, if you want, I can share you the computations.
No, okay.
As far as I understand, A is a Fourier component of the field.
No, chi is Fourier component.
Yes.
No.
Yes.
No. Wait a minute. The second line from the above. Okay. So in the second term, you change k to minus k, and AK is actually a partial Fourier of the field, which depends on time, and it satisfies equation for the partially Fourier transformed field. So this is just partially Fourier transformed field.
Yes.
Okay. So it has both A and a dagger in it, right?
Yes. Yeah. Because we have K and K dagger.
Okay. All right. Okay.
Yeah. The A, which is the creation operation operators is this, and we have this A and A dagger, for instance, in this.
Okay. All right.
I see. Okay.
So are there any other questions? Okay, if no, let's thank Ariel again.
Okay, thanks.
And see you next time.
Bye.
Goodbye.
Bye.
Bye. Thanks for the questions.
Thank you. Goodbye.